Okay, let us start. Good afternoon, everyone. So welcome again to one of our series of lectures that are related to this 1 month celebration set by the United Nations Women and Girls in Science. We are doing it as Women and Girls in Astronomy. And we'd like to thank all of our previous speakers and today's speaker, Ms. Noura Al-Amiri, for giving us this lecture. So she is part of the Sharjah Academy for Astronomy, Space and Technology, and she is very active in the High Energy Astrophysics Lab along with Dr. Antonios and Ms. Mariam Al-Qasimi, that the one that gave us a lecture this past Monday. And today she will be talking about physics of the Large Hadron Collider. But before that, let me give just some bio about Ms. Noura. She is a graduate of University of Sharjah in physics. And I believe, correct me if I am not right, I believe you spent a couple of months at CERN doing some kind of summer internship, and it was an excellent, I believe it was an excellent experience for you to see at hand so how things are being done in these very, very powerful accelerators. So, Ms. Noura, she has a very good background of the subject, and hopefully you will enjoy her lecture, and hopefully there will be no difficult questions to see something like that. Okay, so hopefully things will be fine and so on, and simple for every one of us to enjoy. So please, Noura, you have the stage, inshallah. Tafadhali.
Thank you very much, Dr. Riyad. So, inshallah, I will be giving this lecture, and it will be about physics of the Large Hadron Collider. And what I'm going to do is actually start with some definitions just to get us all in the right frame of mind in order to understand what is matter and what is the matter consists of. And then we will move to, I will move to introduce you to the standard model of particle physics, which is the main theory that is running in the high energy particle physics domain. And then we will see what are the gaps in the models, and actually these gaps were the motivation in order to build this LHC, the Large Hadron Collider. And then I will explain to you what is LHC, what it consists of, what are the main 4 experiments running in the LHC. And then I'll give you a brief about what is this summer student program at CERN, because I believe there will be few physics students around, so just to motivate them to apply for such programs. And then at the end, I have very beautiful picture that I have left it for the end of this presentation. So at the beginning, I have splitted the title into 3 terms or 3 words. The large is indicating how large is this experiment. So we have this accelerator is the largest accelerator in the world. It's like a ring of 27 circumference and has been built 100 meters underground near French-Swiss border, near Geneva in Switzerland. And Hadron, when I say Hadron, just think about it as a proton, as a simple particle, fundamental particles we have. Because in particle physics, we have different classifications for particles, and we have these fundamental particles, and we have the other particles that are as a byproduct of some interactions happening in the subatomic scale. So in this classification, you see in this picture that we have particle classification to leptons and hadrons. Hadrons in here are referring to the protons and neutrons in the atom. I'll explain them later in the upcoming slide. So for now, hadrons are protons, and collider is a system used to accelerate particles and collide them in a specific point where we have installed different detectors in order to capture the interactions happening inside the beam pipe. So Large Hadron Collider is a machine used to accelerate particles into very high energies and then collide them in specific points in order to capture the interactions happening in this beam pipe. So the Large Hadron Collider, as I have mentioned, is the most powerful particle accelerator in the world, and it's built by the European Organization for Nuclear Research, CERN, between 1998 to 2008. It's a collaboration between 10,000 scientists and hundreds of universities and institutions, and also more than 100 countries are involved in this project. It has been built 100 meters underground beneath the French-Switzerland border near Geneva. So in here you see this picture with this yellow circle. It's indicating where is this LHC built there at CERN. And in here, if you can see these different experiments are running there. We have in here CMS experiment and these LHCb experiment and the Atlas experiment and the Alice experiment. These experiments, each of these experiments are doing some specific task in physics. Like I'll explain them in the upcoming slides, inshallah. So this is about CERN, and CERN is the laboratory where the scientists meet, and it provides them with the specific tools or sophisticated tools in order to do their experiments. And the main machine or the main tools that the scientists in this place are required is the accelerators. And accelerators basically is the machine used to accelerate particles into like almost the speed of light. And there are also the detectors that are there in order to detect or capture the interactions happening inside this accelerator. And what is interesting about CERN is CERN is the place where the WWW was born, because like they had to invent this facility in order to allow the scientists to be connected and to share data among them, because it's like a collaboration between 100 countries. So they need this kind of facility in order to be connected all the time to share their results and data. So yeah. And actually CERN and LHC gained like a considerable amount of attention from outside the scientific community. So you'll see a lot of novels, TV series, and a lot of movies and video games where like they were included CERN and LHC as like part of the adventure section of these works. So in here I'm presenting two of the novels that I have read, and were also I read and I found CERN and LHC were mentioned there. The first is the novel written by Dan Brown. It's Angels and Demons. I have read the Arabic version of it, Malaika wa Shayateen. And this novel involves antimatter created at LHC to be used as a weapon against the Vatican. And the second novel is the Flash Forward. It's written by Robert Sawyer. And it mentioned that at the Large Hadron Collider, there was an experiment running to search for the Higgs boson. And as a side effect of this experiment, like what happened is the entire human race loses their consciousness, and a lot of consequences happened there. So because of this high attentions that CERN and LHC got, the CERN website created like a web page in order to answer all the questions that are coming from the people who watched these movies and read these novels, because some of the people after reading these novels and watching these movies, science fiction movies, they think that CERN is the place where a lot of secrets and bad things are happening there, and like people who are working there is doing something very bad to the humanity. So this web page, Fact or Fiction, is a web page used to answer the questions from the general public about CERN and the experiment running there. So this is about how big attention is placed. So what is the big deal? It is a big deal actually, because physicists hope by using LHC they will be able to answer some of the fundamental open questions in physics, like for example, what is the world is made of, and what does hold all of these matters together? What is the dark matter? And are quarks and leptons are fundamental particles, or maybe they are made of another particles? Why are there exactly 3 generations of quarks and leptons in the standard model? And how gravity fit into all of this? We will all of these colored words are like not jargons; they are scientific terminologies, but it will be like clarified for you like in the upcoming slides. So these are the main main fundamental questions to be answered by the physicists, and they're relying on the LHC in order to have the answers to these questions. So let's start from the very beginning. Like suppose that we have this chunk of wood, and this chunk of wood is a matter. So if we zoom in and have like have a lens in order to see what this chunk of food is made of, we will see that this chunk of food is made of atoms that are organized in such a way to create this state of matter. And here we have solid state. So, and if you took this one atom and magnify it, you will see that this one atom is consists of a nucleus with electrons orbiting around this nucleus. And if we zoom in to the nucleus, we will see that the nucleus is consist of protons and neutrons. And if we took one proton and zoom in, we will see that this proton is consist or made of another fundamental particles called quarks. So what is the point that I wanted you to get from this slide is we have kind of particles who are fundamental particles and another particles who are not fundamental particles. Fundamental particles are the particles that you cannot break into another particle. So in here we have electrons are considered as fundamental particles, and quarks are considered as fundamental particles. But proton and neutron are not fundamental particles, because if you took one proton and break it, you will see that the proton is consist of another fundamental particles, which are quarks. So what is the difference between the proton and neutrons in terms of their like the components that create these two particles is protons has 3 quarks and neutrons has 3 quarks as well. But proton has 3 different flavors of quarks, and neutrons have 3 different flavors of quarks. So the protons consist of up, and down quark, where the electrons consist of down, up quark. So this is just these different flavors are indicating the different properties of these fundamental particles in terms of their charges and masses and other things. So these are the fundamental particles, the electrons, and up and down quarks. So we have just met our very elementary particles, the electrons, and 2 types of quarks, the up and down quarks. You can see here we have, this is the standard model of particle physics. It's similar to the periodic table in chemistry, where they have like grouped the different elements in specific groups indicating their chemical and physical properties. We have similar here in particle physics. We have this standard model of particle physics, classifying the particles into different categories or families in order just to simplify the idea for us. Like we have group quarks that they share a specific properties, and we have leptons that are a group of particles who are sharing specific properties, and we have in here the bosons, and here we have the Higgs boson. So from this slide, I just want to add one more particle that is considered as one of the fundamental particles that are creating the ordinary matter that we are made of. So this particle is the neutrino. You see here I have this red rectangle. It's showing the fundamental particles that I am focusing on, is the up and down quark. And we have here the electrons, the very well-known particle to all of us. And we have the associated neutrino of the electrons, the electron neutrino. So neutrino as a particle plays a vital role in reaction that converts neutrons to protons and vice versa. And you can see this reaction that's happening inside the sun in terms or in the form of fusion reactions. That in the fusion reactions we have the hydrogen atoms, the nucleus of hydrogen atoms is fused in order to give us the helium, the very heavy elements, like heavier than the hydrogen, and this kind of reaction will go until it reaches to the iron. And then the fusion reactions will stop. So the neutrino is byproduct of these reactions that's happening inside the sun. And one interesting information is we as a human, we emit about 340 million neutrinos every day, because we have this potassium 40, is a radioactive material in our body. So yeah, I want now, now if I ask you what is the fundamental particles in physics, you should say we have the up and down quarks, and we have the electrons and the neutrino. These are the particles that the ordinary matter are made of. Okay. Yeah. So these fundamental particles that I have mentioned before are bound together in order to form the structures on all scales. What do I mean by the structures on all scales? Like these particles will bind, the protons, neutrons, and electrons will bind together in order to create the material that we see around, the material in different states, solid state, gases, and liquids. So these particles are bound together through forces. The main four fundamental forces are the electromagnetic force and strong nuclear force and weak nuclear force and the gravity. I'm sorry that I have crossed the gravity in here because we haven't detect any kind of effect of the gravity in the subatomic scale or the quantum scale. That's why I have crossed it in here. But gravity is one of the four fundamental forces in the universe or in the physics in general. So these are the four main forces. We have the strong nuclear force and the electromagnetic force and weak nuclear force and the gravity. The strong nuclear force is the force responsible for binding these quarks, and the electromagnetic force manifests itself in the light and radiation that we are using in everyday life, radio waves and X-rays and the signals that we are receiving and the visible light that we used to use it in everyday life. And we have the weak nuclear force is the force responsible for the fusion reactions and radioactivities for the unstable elements. And the gravity is the force that is like manifests itself in falling apples, planets, motion, and satellites. But the difference between the three first forces and the gravity is like we didn't observe the effect of the gravity in the subatomic scale or in the quantum scales. So these forces have another particles that is used to make these interactions. So for the strong nuclear interactions, we have particles that are responsible for making these strong nuclear interactions, and these particles called gluons. These gluons are used to glue these quarks together in order to make this compact space inside the atom, the nucleus. And the photons are the very well-known force carriers for the electromagnetic force. And we have the WZ bosons are the particles or the force carriers responsible for the weak nuclear interactions. Actually, we have predicted that there is a particle responsible for the the gravitational interactions in the subatomic scales or in the quantum scales, but they have predicted it, but they didn't observe it yet. So that's why we are always omitting gravity from the standard model, and when we talk about anything related to high energy particle physics. So these force carriers are particles responsible for making the interactions for every single forces: strong, electromagnetic, weak. So now we reach to defining the standard model of particle physics. Since you now know what are the fundamental particles and what are the force carriers, what are the particles responsible for creating the interactions for every single force. So the standard model of particle physics is the theory used to classify the fundamental particles and describe the three fundamental forces: the electromagnetic, weak, and strong forces. So in here, you will see that there is, as I have mentioned before, in particle physics, we have different classifications of particles. In here, we have these classifications that classifying the particles into two general classifications, into fermions and bosons. We have in the fermions category, we have two families. We have quarks and leptons. From the quarks family, we know the up and down quarks that are creating the protons and neutrons. And from the leptons, we know the electrons and the neutrino as a fundamental particle. And in here, we have the force carriers, or the particles who are responsible for the interaction for every single force. They call them bosons. So the name of fermions and bosons, I'm sorry to mention this, maybe this will be too advanced, but just to give you an idea about from where we got these names. So fermions are particles who obey Fermi-Dirac statistics. It's a kind of distribution used to determine the like how the electrons are filling the energy level. Okay, ignore it. And the bosons are particles who are obeying the Bose-Einstein statistics. It's another distribution used to describe the like a system consists of bosons, the energy of the system. This is just to give you an idea from where we got these fermions and boson naming. And yeah, one more thing that I want to mention about the Higgs boson. Higgs boson is a particle that have been discovered in 2012. And this particle is like considered as very like the important particle because this particle is responsible for giving the masses to the other particles. So this particle is responsible for distributing the masses to another particle through Higgs field. I will not go like into details of this, but you should know now that we have Higgs bosons, and Higgs boson is the particle responsible for giving masses to the other particles. So this is about the standard model of particle physics. We have these different categories, the fermions and bosons, and you now know that we have the fermions category. We have two families. We have the quarks and leptons, and from the quarks, you now know the two flavors, the well-known flavors of quarks, the up and down quarks that are creating the protons and neutrons, and from the leptons family, we have the electron. And the bosons the gauge bosons are the particle responsible for the interactions of the fundamental forces. But we don't have in here, we don't see the graviton, because as what I have mentioned before, the graviton, they haven't detected it yet or observed it in the subatomic scale. So yeah. So the standard model is currently the best description of the world of quarks, leptons, and other particles. However, it leaves many questions unanswered. Like, for example, why we don't include the gravity in the standard model in terms of the graviton, and what is dark matter is made of, because measurements in astronomy implied that 95% of the matter that the universe is consists of is like not known. Because if you see this iceberg representation, we have 5% of the matter that this is the visible matter that we know, that visible matter or ordinary matter that we know about, but 95% of the matter that the universe is made of, we still don't know what are these kind of matters and energy. So yeah, this is one of the questions: what is dark matter, and like. The answers of these questions are either like not known or partially known. So depending upon the experiments that are running at the LHC. So yeah. So it's like, don't let the bright lights fool you. It's like the dark matter, like saying this. It's like, you know a lot about the universe, the astronomical systems, but you should not consider yourself that you have covered and you know everything in the universe, because there is a dark side in terms of dark matter and dark energy. So some of you maybe now are asking like why we study the structure. Why we're studying this kind of structure of matter, why we're going like into these subatomic scales and trying to understand these kind of stuff. We study the structure of matter because the universe is made of matter, is made of this ordinary matter, and the universe is built of this kind of elementary particles, and all of these particles were existed at the after the Big Bang, when the universe was forming. So by studying the particles, the particle in high energy band, we will be able to look back in time, recreating the environment present at the origin of the universe. So from this picture, you see that here we have like different scales. We have time, and we have temperature, and we have the energy. And if you come here, like You see these different scales. In here we have 10 to the power 15, and in here is 10 to the power 2. But in here, I draw a line from this like LHC. You will see that we are here. We are running an experiment in this energy band. It's about the 10 to the power 12, the tera electron volt. So the experiment running at CERN are simulating the environment or conditions that happened after the Big Bang. We're in this time scale. So we study the structure of matter in order to understand the universe, that this universe is made of elementary particles. And by understanding the universe, we'll be able to understand like how the stars formed, and we'll understand like everything around us, and even we'll understand what we are made of. So yeah. And because the particles, like the fundamental particles are tiny and very small, we need a very special tools in order to run such experiments like into high energies. And these experiments consist of the accelerators. And accelerators in general are machines used to accelerate particle into very high speed. It should be like a speed very close to the speed of light, and then smashing these particles together in order to recreate the conditions that were happened after the Big Bang. So by accelerating and smashing these particles, physicists hope to identify their components or create new physics, and then they will discover or explore like the nature in more like detail. So, but the question now is, why do we need to accelerate them to such high energies? Why we need to accelerate the particles into high energies before collide them? Because the energetic particles, when we collide the energetic particles, the energy of collision is transformed into matter in the form of a new particle. Okay, I know that for some of you this will be unclear. But again, the energetic particles, when we collide the energetic particles, the energy of the collision is transformed into a matter in the form of new particles. And this phenomenon is described by the very famous equation of Einstein, E equal to mc squared. E is energy, and m is mass, and c squared is the speed of light squared. So if we want to have this phenomenon to happen, the energy to be transformed into mass, we have to accelerate the particles close to the speed of light. And this will lead to this phenomenon to happen. So I hope you got the idea coming from this equation. So this equation like simply says like the matter is a concentrated form of energy. And these two things are exchangeable. And the main things to have this equation like works, to have the interactions or to have these particles should be accelerated to close to the speed of light. Because you can get it from this equation, E equal to mc squared. So this is the kind of the conditions to have this equation to be run. So I hope you got this, because this is the main idea behind the experiment at the LHC. So far we have covered like what is LHC and where is the LHC as an experiment as it's at CERN, and why we are studying the matter and what is the matter is consist of, what are the elementary particles, what are the force carriers, and what is the standard model, what are the gaps in the standard models. And yeah, this is about the, like I would say, the background about the LHC. So now I can speak about the LHC as a system and machine or a facility. The LHC is designed to collide two beams of protons at 0.9999991 times the speed of light, very high, close to the speed of light. And this kind of collisions are happening at energy, and in total 14 tera electron volt. Tera is 10 to the power 12. And the beams move around the LHC ring inside a continuous vacuum guided by magnets. The magnets used are superconducting magnets, which means that the resistance is equal to 0. And maybe this picture will give you an idea what happened at the LHC. Is we have two beams of particles, the electrons that's coming from this side, and there is another bunch of beam are coming from that side. And we collide these bunch of protons. And if we took two protons and see what happens between these two protons, after the collision, the constituents of the proton will come out. And the constituents are the quarks and gluons. And then the other reactions will happen, like a decay of particles, jets, a shower of particles, and these kind of interactions will be captured by specific tools or detectors distributed in specific points around the ring of the LHC. And these 4 experiments are ATLAS experiment, CMS, LHCb, and ALICE. And yeah. And these 4 experiments are 4 detectors used to detect specific type of interactions in order to answer some of the fundamental open questions or to discover new physics in the field. So the detectors, the main 4 detectors that are running at CERN, the first detector, the ATLAS detectors or ATLAS experiment or ATLAS collaboration. ATLAS is a toroidal LHC apparatus, is one of the 2 general purpose detectors at the LHC. And the main role of ATLAS is to search for the Higgs boson, 2 extra dimensions, and particles that could make up the dark matter. The Higgs boson has been discovered in 2012, and they got 2013 they got a Nobel Prize for this discovery of the Higgs boson. And ATLAS experiment is the biggest, the ATLAS collaboration is the biggest collaboration. The ATLAS detector is the biggest detectors on Earth, I guess. And the good news is in July 2021, the University of Sharjah officially announced it's joining the ATLAS experiment or ATLAS collaboration. And Dr. Rashid from the Applied Physics and Astronomy department is leading this collaboration. And we hope the best for them. And the second detector is CMS detector, the compact muon solenoid. It's one of the 2 general purpose. We consider CMS as a cousin or sister of ATLAS, because what ATLAS is doing, CMS is confirming. Like when they detect the Higgs boson, they need a confirmation from the CMS experiment to confirm their results. And the third experiment is the LHCb, the Large Hadron Collider Beauty experiment. This experiment specializes in investigating the slight differences between matter and antimatter by studying type of particle called beauty quark or B quark. B quark is one of the flavors in the quark family. And the 4th experiment is ALICE, a Large Ion Collider experiment. It's a detector dedicated to heavy ion physics at the Large Hadron Collider. So I just, in here, I gave you a brief about these detectors, but there are lots of very complicated stuff related to these, the structure of these detectors and what kind of experiment, what kind of physics behind these experiments. But just to make it simply for you, I just put you these pinpoints. And now, I'll give you a brief about the CERN summer student program, just to motivate the physics student or any other science student or maybe engineering student to try to apply in such program to get this incredible experience. So CERN provide a unique opportunity for the student to join a day-to-day work of research teams participating in the real experiment. And they will give you a task to work in a real project under supervision of one of the researcher there. And you will work on your project and you will get a results, and then you will write a report and present your results at CERN and then come to present it at the university. I mean, like the University of Sharjah, the university that you are belong to. And beyond the outstanding first-class scientific values, the students get a chance to work in a multidisciplinary and multicultural environment. It was like I can't express like how valuable was the experience, my experience at CERN. So, and it was batch of 2017. I put this arrow. I don't know if you can see me and my colleague Selwa from the university, from the physics department. And really, it's a once in a lifetime opportunity. I don't think that I will have a chance to have similar to this experience, even if I got a chance to go to any internship. I don't know, but CERN is a very unique place to do your like to have like an experience from it. So this is like about the what sort of like projects you will be assigned to if you have applied in this summer student program. I have worked. By the way, my colleague Mariam Al-Qasimi also she went to CERN in 2016, and I went to CERN in 2017, and she worked also on the LHCb collaboration. And the project that I worked on was about systematic tuning of Monte Carlo event generator LHCb using Professor. Professor is a tool, is procedure of estimating systematic error. It's a tool like to reduce the error that are coming from the Monte Carlo simulation. And this is the end of my presentation, and this is the very beautiful picture that I have mentioned it at the very beginning of the presentation. This is beautiful because in this place, this is CERN auditorium, and in this meeting where you see all of these scientists and physicists and guest engineers are gathered for the announcement for the discovery of Higgs boson. And in here, like, I would like to spotlight on the general director of CERN, Fabiola. She was the project leader of Atlas experiment when the Higgs boson was discovered, and because of her successful leadership, they put her as a general director of CERN, and she's the first woman who got this position at CERN, and she's the first person who got they have extended her contract into another 5 years, so she's leading this organization for maybe 8 or 9 years, I guess, until 2025. So, and I don't know, I feel this pictures, I don't know, I feel something are coming from it, and it makes me feel happy and relaxed. And maybe you can see here Professor John Ellis, and I guess Peter Higgs should be here around, but I can't see him. And yes, this is the end of my presentation, and I hope you get benefit from it.
Thank you very much, Nora, for this nice presentation, and I believe you express your warm feelings in this 2017 CERN internship. I believe we will never forget it, as you said.
Yeah.
And by seeing this picture, this is very hard picture, because you see hundreds of scientists, engineers, all working together in this beautiful organization, CERN. So thank you very much for this presentation. It was very light. I can say it was light. I believe my students would have no problem following it, and I would like to open the floor if you have any questions. So please, if you have any questions, you can ask, or you can write on the chat, please. Any questions from the audience, please?
If the students don't have questions, can I ask a question, please?
Yeah, go, Marwan, please.
Yeah, thank you very much, Noura. It was really very bright presentation. Thank you. I noticed that you didn't mention the antimatter particles within the table. I believe if we do that, then it will be an extended table with anti of all of these particles. Is there some reason, or just you want to mention the matter itself?
Because yes, I was focusing on the fundamental particles that are in the ordinary matter that we are consist of. Because the subject of antimatter is very complicated, and I myself can't speak about or explain about. So that's why I just took this simple version of the standard model to give them an idea about the very simplest the very simple picture of the standard model particle physics.
Well known, and mashallah, you can do it, of course, next time. Can I ask another question, please?
Yes.
If we discovered the graviton, so what favor would be given if the question is correct?
Okay, it is a correct question, because they're trying to discover the graviton in order to have the theory of everything, because for now we have unification between the electromagnetic force and the weak nuclear force. They're trying to have the strong nuclear force and as a parameter in that formula in order to have this grand unification theory. And by adding the graviton, they will reach to the theory of everything. This will help us to explain everything around us, because it will include the 4 fundamental forces that are governing everything around us in the macroscopic scale. And then they will have this full view in the subatomic scale or in the quantum scale. Yeah.
Thank you.
Any other question, please? I'm checking the chat, so there are no questions. Okay, so thank you very much again, Ms. Noura. So thank you for this presentation, and I believe you are always faithful to what you request from you, and hopefully, so my student, inshallah, they have benefited a lot from this lecture, from what I see from the chat. So they are all thanking you for this nice presentation. And so this is part of our celebration of women and girls in astronomy, or in general, women and girls in science. So thank you again, Noura, and thank you for the students. Thank you for everyone who participated. And we still have more activities next week, inshallah. So see you next time, inshallah. Thank you very much.
Thank you very much.
Marwan, before you go, don't forget, tomorrow I will bring my students.
Yeah, no. We arrange something beautiful. All students, we would like to announce, even the people here. We do great shows for everyone, and particularly the students of university, inshallah.
Inshallah. Thank you. Thank you very much. Okay, we start at 8 o'clock tomorrow, inshallah.
Inshallah. Is there any bonus, Doctor, for the students? Any bonus, mark bonus?
Yeah, oh, for sure.
How much?
Secret.
Okay.
Okay, see you tomorrow, inshallah. Assalamu alaikum. Shukran. Alaikum.